Bismillah ar-Rahman ar-Rahim. This is lecture 11. This is a continuation of the previous lecture. We were talking about the stability of a differential equation. So the complete solution u of t is built from pure solutions like e to the lambda t times x. And if lambda is real, then e to the lambda t goes to 0 if lambda is negative. Or if lambda is complex, lambda equal to a plus ib, then its real part a must be negative. So e to the at goes to 0, and e to the ibt is bounded because it is equal to cosine bt plus I sine bt. The magnitude of each one of these is 1. So if we take the magnitude of e to the ibt squared, it is cosine squared plus sine squared, which is 1. The question is, which 2 by 2 matrices have negative eigenvalues? So if we take A in general, A, B, C, D, then the determinant of A minus lambda I equals 0 gives the eigenvalues, and the characteristic equation would be lambda squared minus A plus D times lambda plus AD minus BC equals 0. Now the first term, A plus D is T, it's a trace of the matrix, and D is the determinant, D minus BC. So if we look for the roots here, lambda would be solution of a quadratic equation. So we will have this 1/2 t plus minus square root t squared minus 4d. Now since d is the determinant is equal to the product of the eigenvalues, and t is the sum of the eigenvalues, the sum of the eigenvalues must be negative because the real part here of lambda is t over 2, so t must be negative. Okay, so if for stability both lambda 1 and lambda 2 must be negative, so lambda 1 times lambda 2 would be positive. So the rule for the stability of a 2 by 2 matrix is D positive, determinant must be positive, and the trace T must be negative. Here's an example. Which of these matrices is stable? The first one has determinant less than 0, it's minus 2, so it is unstable, does not satisfy the condition that D must be positive. The second one has D equals 2, and the trace T is minus 3, so it is stable, it satisfies the conditions. For the third one, the trace is negative, D equals 0, so lambda 1 equals 0 and lambda 2 is minus 16, so this is stable. Now we come to the subject of the exponential of a matrix. If we copy the solution of a scalar equation, du by dt equals au, the solution is u equals u naught of 0 e to the at. So if we take the matrix equation du by dt equal to au, when u is a vector, the solution would be u of t equal to e to the at times u of 0. To see what e to the at means, we copy e to the x, which is given by the infinite Maclaurin series. So the exponential of x is the series, the infinite series 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. This series converges because each term is smaller than the previous one. So the definition of e to the at then would be, along the same lines, e to the at would be I instead of 1, x becomes a times t, Second term, third term is 1 over 2 factorial at squared. Third term 1 over 3 factorial at cubed, and so on. This series converges and its derivative is always a times e to the at. So e to the at u of 0 solves the differential equation with one quick formula, even if the matrix is not diagonalizable. So if A can be diagonalized, that is, if A is equal to S lambda S inverse, then substitution into the series of e to the at, okay, would give us this. And you see here that S lambda S inverse t times S lambda S inverse t simplifies to S lambda square times t square times S minus 1. So we can factor S and S minus 1 out of all terms in the series, and noting that I is S inverse, so this would be S times I plus lambda t plus 1/2 lambda t squared plus. Then the term inside the bracket is actually the expansion of e to the lambda t. Okay, and this is the exponential matrix, okay, which is a diagonal matrix with e to the lambda 1 t, e to the lambda 2 t, etc. on the main diagonal. This is the solution we obtained before, okay, using the same technique for the difference equations. We can summarize the procedure for finding solution for the matrix equation du by dt equals to au. First, find lambdas and x's. Write the initial condition u of 0 as a linear combination of the eigenvectors c1 x1 plus cn xn. Then multiply each eigenvector xi by its corresponding e to the lambda it. And the solution would be this: c1 e to the lambda 1t times x1 plus cn e to the lambda nt xn. An example on the application of the exponential matrix. Let us find e to the at for a equal to 0, 1, minus 1, 0, an antisymmetric matrix. Note here that a square is minus 1, 0, 0, minus 1. A cube is actually minus of a, and a4 becomes the identity matrix I. So the higher order terms, a to the 5, a to the 6, a to the 7, a to the 8, will repeat a square, a cube, and a to the 4. So we can write now e to the at equal to I plus 8 times t, then 1 over 2 factorial a squared times t squared, and 1 over 3 factorial, which is 1 over 6 times a t cubed, and so on. So if we substitute into the matrix, okay, we will get the first term here. It has contributions from I and from at squared, okay, because a has 0 in the first term, and then from t to the 4 because 0 in a cube in the first term. So what we find here is that this is the series for cosine of t. Similarly, the second term would give us the odd terms, start with t, okay, from a, and 0 from a squared, but from a cube we have minus t cube over 6, and so on from t to the 5. Then this will be sine t. The other terms would be the same as this, but with a minus sign, so it is minus sine t, and this would be again cosine t. So this is e to the at. It comes to this matrix. If we take the derivative of this matrix with respect to time, we see that we will get the matrix A, which we had before, which is 0, 1, minus 1, okay, this matrix A, times the matrix e to the at. So it is A e to the at. So it satisfies the differential equation. Now note that A is skew-symmetric, so A transpose is minus A, and e to the at is an orthogonal matrix. That is, the columns are unit vectors. The eigenvalues of A are I and minus I. The eigenvalues of e to the at are e to the it and e to minus it. That is, the eigenvalues of e to the at are e to the lambda t. And when A is skew-symmetric, e to the at is orthogonal. Example 6. We take the same matrix now and we solve the differential equation du by dt equal to au using eigenvalues and eigenvectors and compare with the matrix exponentials in the previous example. So the eigenvalues of A give us lambda squared plus 1 equals 0, which is lambda 1 equals I, lambda 2 is minus I. The eigenvectors would be x1 is 1 and I, x2 is 1 minus I. So the solution now becomes u of t is c1 e to the it times x1, c2 e to the minus it times x2, which we can put in matrix form. Okay. This is the matrix S of eigenvectors, and this is e to the it, and it is multiplied by c1, c2. Now, if you remember that the initial condition u of 0 is really the matrix of eigenvectors times c. So c is really S inverse times u of 0. We substitute back into this equation. We come up with S e to the lambda t times S inverse times u of 0. And if we multiply the three matrices together, we come up with this matrix. The first term is 1/2 e to the it plus e to minus it, which is cosine t. The second term here would be sine t, and here so we'll have minus sine t and here cosine t again. So again, we came up with the same solution which we found using the exponential matrix expansion. Okay.